So good evening everyone. So today we will start with the plate count. Okay. So in our last class, if you see, we have been discussing about the different types of chromatographic techniques, and over there we have discussed about planar chromatography and column chromatography. Okay. Now coming to the plane count this thing. So what we have basically, suppose we have this planar chromatographic plate. Okay, and what we discussed is that suppose we have the baseline where we have put some chromogenic agents. Now then we have inserted this plate into the solvent. Now the solvent, due to the capillary action, it moves up, and the solvent front, it reaches up to this point, and then we take out the plate. Say for example this. So the distance between this solvent front and where you have applied the chromogens, that is regarded as L. Okay. The same thing if you want to see in the columns. So you will be having a packed column. Okay. Suppose you have started the flow through the solvent. So your mobile phase, it is moving, and the solvent front, it is at the lower end of the column. Okay. So after some time, this front, it will again move down, and the whole column will be it will be having the flow of the mobile phase. Okay. So in that case, if the solvent front, it is within the column, then your L would be something like this, and you are just analyzing the bands within the columns in this case. Okay. However, if you are using the UV detectors and all these things, and you are collecting this solvent at the outlet of the column, and then you are analyzing that, then in that case the L would be the total length of the column. Okay, the total length of the column. Now basically what I want to say is that it is the portion of the column which you are utilizing for the analysis of your analytes. Okay. Now what happens, you are having this, you are getting some analytes, you are detecting the thing, and then you get a graph. In our last class, I have discussed that these curves, if you are analyzing the thing in the inline process, so you will get something like this. You will be getting a peak like this. Okay, and this is the concentration of the analyte. Okay, in paper chromatography, you will be able to see, suppose this dot moves, you will be having a dot, and across the central part there will be a band. Okay, so you will not get a specific pointed dots, whatever you are getting over here. Okay. However, if you change the parameter, it may so happen that you can get a fine point over here, and in the other case, in the column, you can get a very sharp peak. Okay, it may happen, right? Now how this is happening? This is happening because if you look into the black peak, it is narrower, so the resolution of your column system is better in the case when you are having this black peak as compared to the resolution of the column or the plate when you have got the results, got this red colored graph from whatever the column you have got, right? So we can see, even though we are using say same column, by changing the type of the analyte, by changing the mobile phase, by changing the velocity of the mobile phase, we are able to change the resolution of the column. Okay. Now better the resolution, better will be your separation. Okay, right? What do you mean by separation? Separation means you are able to get the components or the analytes in a very narrow peak, and you will be getting getting the thing at almost at one go. Okay, the chromosomes will be eluted out of the system almost at one go, or they will be present in the planar system at a very thin layer. Okay, so the separation would be the better one. Now how do we say that the column is having a better resolution or not? So what we do is that when we have this column, we use a theoretical basis to divide the column. Okay, so when we are dividing the column, what we are doing, we are considering that these are small plate like structures. So you are having small plate like structures. Okay, now these plate like structures which are hypothetical in nature, they are regarded as plates. Okay, and the height or the width of this plate, it is regarded as the plate height. Okay, and the plate height, it is given by H is equal to L by N. What is L? L I have already told you, the length of your column divided by the number of the plates. Okay, number of the theoretical plates. Okay, so you will say that higher the number, lower will be the height, and vice versa. Okay, height means the width of this column, right? Now the number of these theoretical plates, it can be estimated from a chromatogram by analysis of the retention time for each component and its standard deviation as a measure for the peak width, provided that the elution curve represents a Gaussian curve. So what it is saying, you are having these peaks of the analytes which are coming out of the chromatographic system. You are analyzing it. First of all, this peak should be a Gaussian curve. Okay, now what is your TR? Say you have injected your sample at the 0 time, and the peak of the analyte where the curve has reached the peak, the distance between these two, it is given by the retention time. Okay, now there is a standard deviation over here. What is this standard deviation? This standard deviation is nothing but the standard deviation of this peak from the average at each location. Okay, so if you measure the width and then you try to find out the standard deviation, that would be your this standard deviation over here. Okay, now in this case the plate count, because we don't know how many numbers of plates will be there, we also don't know what should be the height of the plate or the width of the plate, whatever you want to say. So we don't know any of this. What we get, we just get this type of curve, right? Now when we are getting this kind of curve, From that curve only we need to estimate, I'm again telling, we need to estimate the number of the plates. Once you get the number of the plates, you can calculate the height of the plates. Okay. Now n is equal to Tr by sigma whole square. Tr I have already told you, you can calculate it from the time axis, and sigma you can find out from the curve. Okay. However, if you see over here, calculating each of the weights over here, it is practically impossible. We cannot do that. Okay. So what is the possible way? The possible way is that, suppose this is your peak, analyte peak. Okay. Now this baseline, it means zero concentration, 0%. At peak, say we consider it as 100% concentration, okay, or 100% height. Now we draw a line at 50%. The width at this 50% is calculated, and it is regarded as W half. Okay, and it is regarded as W half. Okay, so peak width at half height. Okay, peak width at half height. Now when we do this, our equation becomes n equals to 8 ln 2 then multiplied by Tr by W half whole square. Okay. Again, you can see there are a lot of calculations over here. This equation can further be simplified to this equation where n is equal to 16 Tr divided by W base whole square. So what is the W base? The width when you are having the baseline over here, this is the baseline of the chromatograph. The width at the baseline of the curve, it is regarded as the W base, and from there we can calculate the number of the plates. Okay. So usually, as I told you, higher the number of the plates, better will be the resolution power of your column or the plate. Now, when we talk about this, if you see, we are just looking into the curve and we are saying that from here we can find out the number of the plates. But what happens to the nature of the stationary phase? What happens to the properties of the mobile phase? These are not included over here. So this is one of the simplistic models to calculate your what you call the plate height based upon what happens over here is that there is no information over there, right? Now since there is no information, we cannot analyze it. So this is true, this equation will help you when you have already optimized something. Okay, but what about when you have not optimized? So for that we have the another analysis which is regarded as Van Dimter equation. Okay, and it says that the height of the plate, which is also known as the height equivalent to a theoretical plate, HETP, height equivalent to a theoretical plate. Okay, so plate height and height equivalent to the theoretical plate. Both are the same thing. However, in Dimter equation, you have more variables which have been included that may affect the resolution of the plates. Okay. So, what are these? These are nothing but HATP is equal to A plus B by U plus CS plus CM U. What is A? A is nothing but the AD diffusion parameter. Okay. AD diffusion parameter. Now, what is AD diffusion parameter? We need to consider that suppose when we are making a column, it is expected that all the particles, they should be of similar size and shape. However, practically is that possible? Practically it is not possible. Okay. So what you will be having is that you will be having the particles of different size, different shapes. Obviously there will be some there will be some similarity, but what I mean to say is that there would be some deviations from an idealistic character. Okay. So when you are having this deviation from this idealistic character, what it does is that it basically changes the length of the path length of the mobile phase what it has to travel through the column. And this difference in the movement of the path length of the mobile phase when they are moving through the column or the plate is regarded as the AD diffusion parameter. Okay, because it is expected the solvent front they will move all together. However, since there is a change in the path length, so suppose both of them 1, 2, 3, 4, there are say 4 analytes are there. Okay, so the first one it will take a shortest path, so it will be eluted first. Then the second one, say it is taking slightly longer path, it will be eluted second, then third one, then fourth one. Though you have started at the same time and all the parameters they are similar, however, since the mobile phase it has to move different path lengths, there will be a spread. So that can be one of the reason for the peak broadening. Okay, in the chromatogram we are expecting that it should be a pointed line like this, but because of this eddy diffusion it would be something having a Gaussian spread. Okay. Second thing, diffusion coefficient of the eluting particles in the longitudinal direction. Okay, resulting in dispersion. Okay. So for making this understand, what I will do is that I will draw this column in the longitudinal way. Okay, it will be better for you understand. So this is a longitudinal direction. Okay, now any column, I don't know whether you have seen a column or not, it will be having a broad area over here. However, while getting out there will be a narrow opening. Okay, now we are expecting that it will move in a same front. Okay, so from this way we are having this mobile phase which is moving this solvent front or the analyte. Okay, however, when it is getting out there will be a back pressure onto the system also. the solvent or the mobile phase will come out because the pressure, the inlet pressure of the mobile phase is greater than the back pressure. Okay. However, we need to understand this, that there will also be a column back pressure onto the system, and due to this column back pressure, this mobile phase, it is trying to push the solutes in the front, whereas the back pressure, it is trying to move this solute backwards, and because of these two counteracting forces, we will be getting some spread of the analytes within the column itself. Okay. In general, if the velocity of the mobile phase is higher, it has been seen that the broadening, it decreases. Okay. However, again, there is a limit over there. Then the third point is resistance to mass transfer coefficient of the analyte between the mobile and the stationary phase. What we said is that solvent, it is taking the analytes along with it, but it has also got some partition coefficient activity. Okay, because of that, stationary phase is also trying to pull the analytes back into it. Okay, so it is creating a drag force. Okay, so due to this reason, what happens is that okay, this is all the same curve, but just for the sake of understanding, I'm drawing it with another color. Okay. So this portion, it is in the stationary phase, this black shaded area. So when the solvent front is moving, it has moved slightly ahead. However, still the stationary phase, it is trying to hold up the solute molecules within itself. Okay, and this is creating a drag, and this drag also is creating the broadening of the peak. Okay, and lastly, the speed of the system, if you see, it would be a combination of over here and over here. Okay, now in open tubular capillaries, when we say open tubular capillaries, open means there will be no stationary phase packing in the capillary system. As I told you yesterday, there will be having a layer of the stationary phase on which are attached onto the surface of the this capillary electrodes, inner surface of the capillary electrodes. So in that case, the A term, it would become 0. Okay, the A term, it would become 0. So in capillary chromatographic techniques, you will find there are no A terms. Okay. In packed columns, however, the multiple distinct routes or channels, they exist through the column packing, which results in the band spreading. In the latter case, A will not be 0. Okay, column where you are having any kind of stationary phase, you will find stationary phase in the bulk, you will find that A term will not be 0 over there. Okay, however, you can reduce this A factor by preparing homogeneous beds. Beds mean column beds. Okay, homogeneous sized particles. If you use it, and you can try to make the bed with that homogeneous particles, then you will be getting the things in a proper manner. The A factor would be less. However, you cannot make it completely zero. Okay. The form of the Van Dimter equation is such that HTP achieves a minimum value at a particular velocity. At this flow rate, the resolving power of the column is maximized. So, if you try to plot HTP versus the velocity of the mobile phase, what you will get, that initially it will be very high, then it will move to a minimum point, and after moving to the minimum point it will again increase. Okay, so that would be the best resoluting what you call parameter, or the mobile phase velocity for that analyte, if you want to do the analysis. Okay, so this HTTP, you need to understand is that it has to be calculated by doing several trials. When you get a column, and if you want to analyze a specific analyte, then you have to do a certain number of trials, so that you can find out what is the best resolution of your this chromatographic column, so that you can work in that way. Okay. Now, next we get into the chromatographic techniques. So the first technique is the paper chromatography. So it is a type of planar chromatography. Herein your partition, it is taking place, and it is a type of partition chromatography. Okay. So what happens? Paper chromatography, it is an analytical method used to separate colored chemicals or substances. Okay. It is primarily used as teaching tool, having been replaced by other chromatographic methods such as thin layer chromatography. Okay. A paper chromatography variant, two-dimensional chromatography, involves using two solvents and rotating the paper 90° in between, and this is useful for separating complex mixtures of compound having similar polarity, for example amino acids. Okay. The setup has three components. The mobile phase is generally a mixture of non-polar organic solvents. The stationary phase is polar inorganic solvent, that is water, and lastly the paper, which is used as the support for the stationary phase. Okay. So the polar water molecules are held inside the void space of the cellulose network of the host paper. So what it wants to say and why it is important, if you see, it is mainly used as the teaching tool. Okay, then why it is needed? If you want to go for better chromatographic techniques, it comes with a cost. You can definitely use better chromatographic techniques, but the problem would be, are you capable to spend more money while you are in the early stage of your research? Okay, if you are not, paper chromatography gives you an indication what you should be expecting from your analytes. Okay, So that would be the first step to understand how your analyte system or the samples they may be behaving. Okay, say for example you want to find out which is the best mobile phase. If you want to go for the liquid chromatography, it is also a partition chromatography, but you need a column over there, you need very high grade solvent, you may not have access to that. So initially you can run this over here, you can select the best solvent system over there. Okay, now what it says is that when you have the filter paper, herein we use the filter paper actually. So you dip the filter paper in the water. So what will happen? Due to the capillary action, the water will be absorbed within the filter paper and it will be completely wet. So we have this filter paper, say I have dipped in water, it is now completely wet. Now before dipping it, I have made a line with a pencil. Okay, now on this line I will be adding my analytes. Okay, then I will be putting this chamber, this system, paper system, within a chamber such that the solvent level or the mobile phase level, it is just below this marked line. Okay, so what this solvent will do, it will try to move up. Another important thing, it needs to be covered. Okay, so the solvent, it will try to move up, and while it is trying to move up, it will make the analytes within your sample mixture to move towards the upper side. Okay, and after some time you can calculate the, you can take the picture, or if it is an invisible analyte, you can use some color element to visualize what where your analytes are there. Okay, herein we have also discussed about this two-dimensional chromatography. So what it is done, say for a particular period you have run this mixture, so you have got some peaks like this. Now what you do, you rotate it by 90 degree. Now your proper chromatography, it is having all these peaks. Not at the same level, sorry. Say one has moved somewhat upper, the other is somewhat at a down position. So you will be having like this. Okay, now you run the solvent in this fashion. Initially it was there in the fashion in one dimension, so say this is x, this is y. Okay, so now when you have moved it, your y has come down and this is your x. Sorry, other way around. This would be your y and this would be your x, right? Now when you are running the solvent again, if this analyte is made up of complex mixture, it will now separate over here. Okay, here also if possible, it may so happen that when it is coming over here like this, when you are running the solvent, it may have two spots, say AB. Okay, when you put it in the 90 degree, they will be resolved. Now you are looking from this angle, right? Now see, they have resolved. So this A and B, they are appearing at two different locations. Now even in this A and B, if there are certain other mixture components, they will be again moving or separating from each other. Okay, so to make this clear, let us take this example with a simple one. Let us take only one Listen, we have taken one sample. We have got A, we have got B. When we move it 90°, your B will be here, A will be here, A and B. Again, when you run, they will be separating over here. Now the trick is that the mobile phase in the first run and the mobile phase in the second run, they should be different. Why? When this A and B, it has been separated, if A is having another mixture, say C plus D, they are having same kind of lipophilicity, okay, for the same solvent, and hence both C and D in the spot A, they have appeared at the same place. Now you have to segregate it based upon the change in the lipophilicity. Now that can be done when you can change the mobile phase. Okay, so in that way, this 2D chromatography, it helps you in segregating complex mixtures. Okay, analytes from the complex mixtures. Now we have this retention factor. What is this retention factor? Retention factor, it is defined as the ratio of the distance traveled by the solute to the distance traveled by the solvent. Okay, suppose this is the solvent front and you have this spot over here. This distance is the solvent, say what do you call, this is the solvent front, say R sol, and this is the R solute. Yes, अच्छा दोनों solute आ जाएगा ना. ST, let's make it ST. So your RF would be equal to R of ST divided by R of solvent, solute by solvent. Okay, so this is regarded as the RF. Okay, now RF values, they are expressed as a fraction of 2 decimals. That means say 1.22 and so on. Okay, the RF value of a solution is 0, then it means solute remains in the stationary phase and thus it is immobile. 0 means this R of ST, it has moved on the starting line. It has not moved from the starting line. Okay, so this R solute, it will be 0, whereas the solvent front, it has moved, so we will be getting a 0. RF value equal to 1, it means the solute, it has a very high liking for the mobile phase and it does not have any affinity towards the stationary phase, and hence it has moved along with the solvent. Okay, so it has no affinity for the stationary phase and travels with the solvent. So for example, if a compound travels 9.9 centimeter and the solvent front, it travels 12.7 centimeter, the RF value would be 9.9 divided by 12.7, which is given as 0.78. Okay, now this RF value, it would be dependent on the temperature and the solvent that we have used in the experiment. So all the chromatographic techniques has to be done under certain specific temperatures. Okay, if you change the temperature, then you will be getting different results altogether. So this is how a typical paper chromatography setup it looks. So if you see, this is the line. So just beneath this line we have made this thing, and then see, from a single point we are getting number of chromatograms. Okay, so this is the schematic diagram. So this is the solvent front, this is the paper which has been what do you call, soaked in water, and your chromatograms, it may look like this. Okay. Now types of paper chromatography: descending, the type which we have discussed, This is ascending. Now how you will be having the descending one? Let's place for the solvent over here. Then there is a support bar. This is the support bar, and then you will be having your paper something like this. So the mobile phase, it will be moving like this and then moving like this. So this would be creating a descending paper chromatography, and where you will be placing your sample spots, it will be somewhere over here. That would be your starting point. Okay. Next, ascending, I have already told you the point which we have discussed. This is the ascending one. Then we have ascending, descending. It is very simple. Again, all of this will be done within a closed chamber. So initially ascending, then descending, ascending, descending paper chromatography. Okay. Then we have circular chromatography. In the circular chromatography, so I am talking about the top view. At the center you will be putting the drop, and this drop, it will be moving in all the direction. So how will be the setup look like? This would this blue color, it is your paper. Then you will be having solvent over here. If you see, there is a small channel. Through this small channel, solvent will be present within this what you call tubular structure, and this black what you call marking, it is a wick. Okay, just like the lamp wick, there will be a wick, and then on the top of that you place your paper. Okay, now at the central point, it is getting the solvent. Now this solvent, it will try to move towards the outer diameter of the paper, and while it is doing so, the chromatogens, it will be forming circular bands all throughout. Okay, so maybe we can discuss this one at a later stage, or maybe we can also discuss 10 minutes at the end. Let us discuss. So thin layer chromatography, what happens over there in the thin layer chromatography? In the paper chromatography, the paper used to be the only base. Okay, however, herein we need some adsorbent materials. Okay, now for this adsorbent material, we need a base. So what can be a base? Your glass slide, whatever you are using in the laboratory stuff, it can be a plastic, or it can be an aluminum foil. So whatever you are using in the common day life, you can use those as the base. Any solid plate like structure can be used as a base, and over that we usually put a thin layer of the adsorbent material. Okay, so what can be the adsorbent material? This can be the silica gel, aluminum oxide, or cellulose suspension. Okay, and this layer of the adsorbent, it is known as the stationary phase. Okay, so what you have, suppose you are having this plate. On this plate you have put a thin layer of the adsorbent material. Okay, so suppose this one is your glass slide. Then you have prepared a silica gel suspension, you have poured it and then you have leveled it. Now once you do that, what happens? You get a thin layer of that adsorbent layer onto the system. Then you take it and then you dry it within an oven so that the water stuffs they can evaporate out, and then we need to activate the system. The activation is usually done at 110 degrees centigrade. Okay, now just like paper chromatography, what you have done, you add your mixture and then you put it into the solvent system, and by the process of your partitioning you will be having this separation. Okay, however this is a planar chromatographic technique. Okay, in general commonly you will find the silica gel. It is used in most of the cases. In most of the laboratories, silica gel is used, and usually the non-polar mobile phases like heptane, they are used for the separation. Now, these systems, because if you see most of the analytes, you may not be able to visualize them properly. So in that case, what will happen? How will you see the system? In those cases, what happens is that there are certain materials which are called phosphor, and these phosphors they give fluorescence under a specific light. So there are certain phosphors like zinc sulfide, okay, which shows fluorescence when they are visualized under ultraviolet light. Okay, so what you can do is that after you have run the TLC plate, what you need to do, you put it into the UV chamber, and since these phosphors are present all throughout the plate, all the plate they will be glowing, and where your analytes are present, they would be appearing as black dots. So they will be appearing as black dot. Okay. So otherwise, what you can do, you can use some chemical processes. So like say you have protein. We know that protein reacts with ninhydrin. So if it reacts with ninhydrin, it will give us a blue color. So in that case, if we spray ninhydrin solution onto the plate, it will be giving a blue color. So for visualizing the analytes, either we can go for this phosphorus, or we can go for the chemical reactions which will generate some color, and in that way we can visualize the separation of the different analytes. Okay, so RF I have already told that it is the retardation factor, and we have already discussed in the paper chromatography. Another important thing is that while we are performing the TLC, we apply a sample of known compound. Okay, suppose you are expecting a specific analyte A. If you want to see whether that A is present in your mixture or not, then what we can do, we can get the standard chemical and we can also run it parallelly. So if our standard, it has moved say up to this distance, and if we get another peak or another spot beside that beside the standard, then we can say that that material is also there. Okay, the analyte what we are expecting in the sample, that is also there in the mixture. So in that way we can identify whether an analyte is present or it is not present. Okay, Nowadays, we can also automate the whole process. Okay, usually this TLC it is done manually, but we can do it um, using an automated process, and that automated process it is regarded as HPTLC. Okay, so high performance TLC, where you get all these TLC plate which have been made already in the industry, and they will supply you, and you just have to run it in your own lab. However, the cost will be slightly higher than the normal TLC plates. Okay. Now, preparation of the TLC plates, usually they are commercially available. Okay, so these are usually prepared by mixing adsorbents such as silica gel with a small amount of inert binder like calcium sulfate, which is act as a which will act as the binder. Okay, and water. The spread, this mixture is spread as a thick slurry on an unreactive carrier sheet, usually glass, thick aluminum foil or plastic. The resultant plate is then dried and activated by heating in an oven for 30 minutes at 110 degrees centigrade. The thickness of the absorbent layer is usually 0.1 to 0.2 millimeter for analytical purposes, whereas for preparative purpose it is thicker and it is in the range of 0.5 to 2 mm. Okay, so preparative we have seen that it is for the pure isolation of the compounds. Okay, now you have the plates, you have activated the plates, you put in your mixture samples, then you put it into the solvent, then see this is the solvent front, it is moving, and while it is moving, the what you call the analytes within the samples, they are getting separated. Okay, and after you have done this, we can see from here that we are having two analytes in all the three samples. Okay, now adsorbents and solvents, what are the different adsorbents and what are the different solvents which we can use for the TLC. Okay, and then there are some common developing reagent for paper chromatography which can also be used in the TLC. Iodine vapor. So what it does, organic bases give brown spots when you place the TLC plates or the paper chromatogram into the iodine vapor. Okay, then potassium permanganate solution in acetone or water, it is regarded as the general reagent. It gives a yellow spot or pale spot on the pink background. Then we have bromocresol green. Acids give yellow spots on the green background. Then ninhydrin, it is used for the amino acids which give purple spots on when you are hitting the plate or the paper. Okay. Then we have sodium nitrite, followed by 0.1% N1-naphthyl ethylene diamine dihydrochloride in 1 molar HCl. So we use it for sulfonamides, which give purple or the red spots if primary aromatic means they are present. Then we can use these other reagents also for this for determining these cardiac glycosides, or if there are any aldehydes or ketones. Then there is a drag and drops reagent which can be used to analyze alkaloids which may be present in the mixture. Okay, and they give either brown or orange spots. So with this we complete TLC and the paper chromatography.